Now we're going to look into how we find the values for an inverse function, or a formula for the inverse function, or the graph for the inverse function, given the needed information on the original function f. So starting with a very simple situation, we know that f is a one-to-one function and that its value at 2 is 9, and we want to know what is the value of the inverse function at 9. And here is simply applying the definition. If the function is one-to-one, saying that f of 2 is 9 is exactly the same as saying that 2 is f inverse of 9. So in other words, f inverse of 9, which is what we're looking for, is 2. Okay, let's look at something slightly more complicated. We consider the function f of x is x plus cosine x, and first we want to know if it's one-to-one. It's not obvious unless we can draw the graph and try to use the horizontal line test. But one other criterion that we have is that if a function is monotone, in other words, either increasing on its domain or decreasing on its domain, then it should be one-to-one, while assuming that the domain is an interval. And here the derivative is 1 minus sine x, and since sine x is between negative 1 and 1, 1 minus sine x is always at least 0. The only zeros are isolated, and therefore the function is increasing on the real line, and therefore one-to-one. So knowing that it's one-to-one, we may ask what is the value of the inverse function at 1. Well, one way to rephrase that is to say, for what x is f of x equal to 1. And here it's easy to observe that if you plug x equals 0 in the function, you obtain 0 plus cosine of 0, and cosine of 0 is 1. So that means f of 0 is 1, which rephrases as f inverse of 1 is 0. Okay, turning to the question of how we find a formula for the inverse function. Let's take the one-to-one function 3 minus 2x. It is one-to-one because it is decreasing, right? The derivative is negative 2, so it's decreasing on the real line. In fact, the graph is simply a line of slope negative 2. And therefore, we might want to ask to find a formula for the inverse function. And to do that, we just go by the definition. For a one-to-one function, y equal f of x is equivalent to f inverse of y equal x. So what we're going to do is write y equal f of x. So y equals 3 minus 2x, and then solve for x. If we solve for x, what we're going to obtain is f inverse of y. So in this case, if I start from y equals 3 minus 2x, I subtract 3 on both sides, I get y minus 3 equals negative 2x, divide by negative 2, I get x is 3 minus y over 2, which means that f inverse of y is 3 minus y over 2. If I want to rewrite the function as a function of x, of course I replace y by x. Right? The name of the variable doesn't matter. So if you're more comfortable with the variable x, you can rewrite that as f inverse of x is 3 minus x over 2. Now you see that in general this is really just a strategy we're going to apply if we want to find an algebraic expression for the inverse function of f, knowing an algebraic expression for f. And hopefully knowing that f is one-to-one, even though we don't necessarily need to know in advance. So we're going to write y equal the function f, and then solve for x. And if we can solve that in a unique way, then that will prove both that the function was one-to-one and give us an expression for the inverse function. So for instance, if we're looking for the inverse function of f of x equals 4x minus 1 over 2x plus 3, I'm not going to assume that we know that it's one-to-one, but we're going to see if we can solve for x when we set y equal f of x, solve for x in a unique way, and that will give us our answer. Notice that this function is defined for all x except when 2x plus 3 is 0, because we don't want to divide by 0. So the domain is all the real line except negative 3f. If we were to look for the range, this is a little bit trickier just looking at the expression for f, but we'll see that if we find the inverse function, that will also give us a range of f. So we do what we talked about. We write y equal f of x, and then we're going to solve for x. So to do that, first we multiply both sides by 2x plus 3. And we get 2x plus 3y equal 4x minus 1. Then multiply things through and put together the terms that contain x. So we're going to have 2xy on the left-hand side and 4x on the right-hand side. So factoring out x, and the 2xy gives me x times 2y. And then the 4x on the right-hand side becomes negative 4x on the left-hand side. So I have x multiplied by 2y minus 4. And then for the terms that do not contain x, I have negative 1 that is already on the right-hand side, and 3y that I will move to the right-hand side and becomes negative 3y. Dividing both sides by 2y minus 4 and then multiplying top and bottom by negative 1, I obtain x is 3y plus 1 divided by 4 minus 2y. And so I started from y equal f of x, and I obtain x equal a function of y, and that's by definition f inverse of y. Because I have found a unique formula for x as a function of y, that means that the function f was 1-to-1, and this is the expression for f inverse. So f is 1-to-1. Going back to the question of the range, its range is the domain of f inverse. And f inverse is defined everywhere except when the denominator 4 minus 2y is 0, in other words, except for y equal 2. So in other words, the range is the domain of f inverse, which is all the real line but 2. Now let's take a look at what we can say about the graph of the inverse function if we know the graph of a 1-to-1 function f. If a point of coordinates AB is on the graph of f, what that means is that B is equal to f of a, right, just like on the picture. But if f is 1-to-1, we can rephrase the equality B equal f of a as f inverse of B equal a. Saying that f inverse of b equal a is really the same as saying that the point of coordinates BA is on the graph of f inverse. So, if I draw the line y equal x, you see that the point of coordinates BA is simply the reflection of the point of coordinates AB about the line y equal x. And what that means is that for each point of coordinate AB on the graph of f, the reflection about y equal x is on the graph of f inverse. So in other words, the graph of f inverse is obtained from the graph of f by a reflection about y equal x. Right, so this is exactly what I just said. For a 1-to-1 function, if I know the graph of f, I can obtain the graph of f inverse by reflection about the line y equal x. So let's look at the example where f of x is x squared restricted to the positive reals. Then here is a graph. Certainly it passes the horizontal line test, and this is a 1-to-1 function. And so to obtain the graph of f inverse, we're going to draw the line y equal x and take the reflection of the graph y equal x squared about that line, and this is what we obtain. And probably you recognize the graph of square root of x, and this is not hard to see that this is what it is algebraically, because y equal x squared means that x is plus or minus square root of y, but x is positive, so x has to be positive square root of y. In other words, here I have f inverse of y equals square root of y. However, note that on the graph we have y equal f inverse of x, right? So the discussion we have had about how you obtain the graph of f inverse is when we write y equal f inverse of x. In other words, I write the expression for f inverse in terms of the variable x. Right, when I have f inverse of y is square root of y, all I'm saying is that f inverse is a square root function. So the inverse function here is a square root function, y equal root x. Now in the next video we're going to talk about things that are more related to calculus of inverse function.